Hello and welcome back to the chapter about residence time distribution. We learned in the previous video how to define the RTD. Now we take a look at how we can determine the shape of a E of t and f of t curve, and also how ideal flow patterns help us to do that. Various parameters influence the shape of such a curve. First of all, one major influencing factor is of course the equipment itself. The type of equipment strongly influences how long the material remains inside and how it is mixed and moved. Think of all the different equipment you already know, even if they are for batch processes. You will immediately recognize that the flow patterns inside can be very different. The function of the equipment is a major factor for the flow regime inside. By function, I mean, what do you want to do with the equipment? Do you want to mix, granulate, etc.? For a blender, the goal is easy. We want to blend. Therefore, we can assume that there is a lot of mixing going on. For a granulator, on the other hand, the goal is to create granules, which help to avoid segregation, increase flowability, etc. So the function would be create granules. In order to do that, we need to create either flow and shear forces in the wet granulation process, or we need to create pressure for compaction in a dry granulation process. Both systems create completely different flow regimes while still having the same function. The flow regime in the wet granulation process can be very similar to that of a blender and also a dryer. The material is the second major influencing factor for the shape of the curve. Is the material cohesive or free-flowing? What is the mean particle size? And is there the risk of segregation due to size differences? What is the shape of the particle? These, among other parameters, play a significant role in the form of an RTD curve. Before we look into the ideal world, let's look at a real RTD curve, derived from a measurement. As you can see, the curve does not look very nice. Usually, the interference from the powder flow, the type of measurement, etc., is relatively high, and the fluctuations can be significant. Nonetheless, these measurements are pretty reliable. After data treatment and fitting of a function, you would receive a curve that looks like that. You will learn how to measure such a curve in another chapter. First, we start with the plug flow reactor. You should remember what happens in a plug flow reactor. A plug is transported through a reactor without mixing. The bulk of material that entered the equipment together also leaves it together. If we now add a tracer at a time equals 0, E of t is our impulse response function. So let me depict that for you. We have our x and y axis. Time t is the x-axis, and on the y-axis is E of t. You remember, E of t is the differential distribution function, or exit h distribution. So if at t equals 0 our bulk enters the reactor, it will leave altogether at a later point in time. This time is equal to tau. This is because in this ideal case the mean residence time is the time at which all material leaves the reactor. So the function would look like this. Therefore, E of t is the Dirac delta function over tau minus t. The Dirac delta function is always 0 except at 0 where it is infinite. This means that it always displays exactly like this. It is always 0 except at tau where it is infinite, because with the term tau minus t we move the function towards the point tau. F of t is the corresponding step function. F of t is always 0 until it jumps to 1 at t equal to tau. This ideal flow behavior almost never happens in real-life applications. Nonetheless, you will often hear the term plug flow in discussions about continuous operations. From a regulatory point of view, obviously this seems ideal at first glance. No mixing, you always know exactly where your material is, but also here reality shows that a bit of mixing and delay in the flow is very often a good thing. This helps to dampen disturbances and allows more flexibility with the mass flow rate. We will talk about that later in more detail, but before we do that, let's look at our next ideal flow reactor, the continuous stirred tank. As you remember, the continuous stirred tank has the opposite behavior to the plug flow. The bulk that enters at time 0 is immediately mixed perfectly with all the material that is already inside the tank. If we again add our infinitely small tracer impulse at t equals 0, we get again an impulse response function to our tracer pulse entering the system. Again, we have time on the x-axis and e of t on the y-axis. The exit H distribution looks very different from the plug flow reactor. The concentration in the flow at the outlet starts at a moderate level immediately and is slowly descending. Only after an infinite time period will all material have left the reactor. Let me write that down as a mathematical function. E of t is defined as 1 divided by tau multiplied by e to the power of t, the time, divided by tau. Here tau is again the mean residence time. Tau is dependent on the flow rate and the size of the vessel. Remember, it is defined as a volume flow rate divided by the reactor volume or a mass flow rate and mass respectively. F of t is defined by e of t's integral after dt from 0 to t. Therefore, it is 1 minus e to the power of minus t divided by tau. What happens now at t equals tau? So after the mean residence time has passed. If we quickly calculate that, we see that 63% of the tracer have left the tank. Think back to the plug flow reactor, where 100% has left the reactor at t equals tau. Now, let's look at what happens if we have a cascade of these continuously stirred tanks, a number of continuous stirred tanks that are in series. For our assumption, the holdup or total mass in all tanks stays the same. This means that with every tank we add, the volume of each tank gets a little bit smaller. I have to point that out because tau will stay the same for the equation for E of t. This is independent of the number of tanks you choose. E of t is therefore defined by this equation. F of t is the integral of that function, and as you can see here, it has become already quite complex with regards to the math. Depending on your background, this might be already too much, but for this course, this does not matter. The important thing is that you understand the shapes of the curves and how the ideal reactor types are connected. To that end, I prepared this graph for you. What you see here is t on the x-axis and E of t on the y-axis. To begin with, I set the mean residence time tau to 1.5 minutes. And I included the E of t function for the stirred tank cascade in green and the plug flow reactor in blue. We start with only one reactor, so n equals 1. The curve that results from this is the one for the continuous stirred tank, the plug flow reactor with the same volume and volume flow in blue. If now I increase n to 2, you see that the shape of the curve changes significantly. There is a delay until the tracer reaches a maximum, and the decay after the peak is more prominent. Please now look closely at the position of the peak. It is a little bit before 1 and not at tau, the mean residence time. If now I further increase the number of tanks, this effect intensifies with 3, 4, 5 and more tanks. For the sake of this example, I went to 130 tanks. So now looking back at the resulting curve, you can see that with an increasing number of tanks, the resulting curve looks more and more like the plug flow reactor. With an infinite number of tanks, the curve would look exactly like the one of the plug flow reactor. Let's now take a look at the influence of tau on the shape of our exit H distribution. Tau influences the curve in a different way. I have changed the settings back to the continuous stirred tank where n is 1. If I now increase tau, the curve starts at a lower level and also becomes flattened and more distributed. You also see that the position of the impulse response function of the black flow reactor moves as well. This is because the residence time tau determines the position of the pulse response. If I decrease tau, we can observe the opposite trend. The curve starts at a higher level and the descent is steeper. If now I increase n to 2, meaning we have 2 continuously steered tanks in our cascade, the shape of the exit H distribution changes tremendously, as we have already observed. If I increase or decrease tau, you see that the distribution narrows with smaller tau and tends to look more like the plug flow response. Increasing tau makes the distribution E of t flatter. When now I again increase n to 130 and decrease tau, the curve looks almost like the plug flow impulse response. And it is also at the position of the plug flow response function in blue that you see here. If I increase tau, the curve still has its peak very close to the plug flow peak, but it grows broader. If I now increase the number of tanks further, the curve would once more become narrower with the center at tau. So these were the theoretical or ideal equations for the exit H distribution, from only 3 ideal cases. There are of course more derivatives of these cases that you can find in literature. Now we can compare the flow pattern of the continuous steered tank cascade with the real flow patterns I showed you before. You see that the patterns are similar. Usually in real equipment we see long tailing. That is this part here. This can be combined with a substantial increase in the beginning here. The tailing can be caused by dead zones in the equipment. These are zones of stagnant flow where the material gets caught, and for that reason the release out of these zones gets prolonged. These zones are important to know for every piece of equipment in order to understand the overall impact on the residence time distribution of a continuous process, especially when you want to consider the complete plant. Once again, with that, I'd like to thank you for your attention and see you soon.